Welcome back, everyone. In this video we're going to start talking about optimization, which as it sounds is finding the optimal solution to some problem. And we can see how this is going to tie in with the topics we've been talking about, because finding an optimal solution usually boils down to either finding a maximum or minimum value to some function. And some examples, real examples, would be a business person might want to minimize the costs and maximize their profits. If you are traveling somewhere, you're going to want to minimize your transportation time. Or if you are a farmer and you're creating some kind of enclosure to keep your animals in, you're going to want to maximize the area for the smallest amount of fencing. And so this is very clearly a maximization or minimization problem. And we're going to be using the techniques from the last video of finding the global or absolute max or min using calculus. So for our example, let's find the dimensions of a rectangle that has a perimeter of 100 meters whose area is as large as possible. And this example is not as exciting as the examples I just talked about, but I think it's better to start with something a little bit simpler before we move on to the more in-depth kinds of problems. Now in this problem, our goal is to maximize the area of this rectangle given the constraint that the perimeter is exactly 100 meters. And it always helps me to draw a diagram, even if it's as simple as a rectangle. And so let's draw a rectangle, and the goal is to get the maximum area for this rectangle. And that can be a little bit tricky because I don't even know what the sides of this rectangle are. Now, even though I don't know the dimensions of this rectangle, I can assign each side a different variable. And so I'm going to call one of the sides x and the other side y. And the opposite side of x is also x, and the opposite side of y is also y. And so I only need two variables, one for the length and one for the width. And so the area of this rectangle is x times y, whatever x and y are. And this is the equation that we want to find the maximum value of. But there's a little bit of an issue here because all of the equations that we've been finding the maximums or minimums of have only had one variable in them. And this is an equation with two input variables, that being x and y. And I'd much rather work with one variable. And if I look back at the problem, let's think, is there any way that we can relate x and y together so I can get y in terms of x or x in terms of y? Well, looking back at the problem, the perimeter of this rectangle has to be 100 meters. That is fixed, that is set in stone, that can't change. That is one of the constraints. It's the only constraint. And because the perimeter is 100 meters, I know that 2x plus 2y is equal to 100, because two of the sides of this rectangle are x, and the other two sides have a length of y, and if I add all those sides together, I should get 100. And from there, we have a nice equation that we can solve for either x or y. I'm going to choose to solve for y, and when I do that, I'm going to get that y is equal to 100 minus 2x, all divided by 2. And I can simplify that into 50 minus x. And so y is 50 minus x. And so if I look back at the area of this rectangle, the area is x times y, but now I know what y is in terms of x. Since y is 50 minus x, the area of this rectangle is really x times 50 minus x, which I can simplify into 50x minus x squared. And so I now have the area of this rectangle in terms of one variable, that being x. And one thing that'll help us for later is to take note of what the possible values for x could be. And I think it's clear that x can't be negative, because it wouldn't make sense to have a rectangle with a length that is negative. But the largest x can be is 50. That's because the perimeter of this rectangle is 100, and so if x is 50, that means one side of this rectangle is a length of 50, and with how rectangles work, the opposite side would also have to have a length of 50. And that right there would have used up all my perimeter. I wouldn't have any more perimeter to use. And so x cannot be possibly larger than 50 meters. And so x is between 0 and 50. And now that we've got all that figured out, we have a problem that is more reminiscent of the types of problems we've been doing very recently in this course. And that is finding the maximum value of a function, that being 50x minus x squared, on a closed interval, that being from 0 to 50. And the way that we find the absolute max or absolute min on an interval, on a closed interval, is by taking the critical points of this function, the endpoints on this interval, and then plugging all of those into the function, and whichever one of those gives the highest value is our absolute maximum, and whichever of those gives the lowest value is the absolute minimum. And we're looking for the absolute maximum, so that's the only one we're going to care about in this problem. But first, let's find the critical points. And for that, let's take the derivative. And the derivative of 50x minus x squared is 50 minus 2x. And to find the critical points, we want to know either when this is equal to 0 or when this is undefined. And now 50 minus 2x is not going to be undefined anywhere, so that's not an issue. So let's set it equal to 0 and then solve for x. And fairly easily, we can find that x is equal to 25. And this is one of the critical points, which might be our answer, but is not guaranteed to be our answer until we do a little bit more work. And to find the global maximum, we're going to take this value of 25, and we're going to take the endpoints of the interval, that being 0 and 50, and plug all three of those values into the function a of x. And we're not plugging these into the derivative function, we're plugging these into the function for the area, because that's what we're actually trying to maximize here. And so if I plug in 25 to the area function, and I simplify that, I'll get 625. And if I plug in 0, I'm going to get 0. If I plug in the other endpoint, which is 50, I'll also get 0. And between 625, 0, and 0, which one of those is the largest? Well, very clearly it's 625. And so the absolute maximum of this function occurs when x is equal to 25. But even now that we've found the maximum is at x equal to 25, we still have to make sure that we've actually answered the question. And if we look back at the problem asked us to find the dimensions of the rectangle whose area is as large as possible. And we know that x equal to 25 gives the maximum area, but the dimensions include not just x, but also y. And so if x is 25, what would y be? Well, we know from earlier that 2x plus 2y is equal to 100, because that's how we related x and y together. And if x is equal to 25 and you plug that into the equation, you'll find that y is equal to 25. And so the actual answer to this question is that the dimensions of this rectangle that give the largest area for a perimeter of 100 meters is a rectangle of 25 meters by 25 meters. And so this rectangle is not just a rectangle, it's actually a square. And that was a long problem. There were a whole lot of steps to go through. We first had to figure out what we were actually trying to maximize, which was the area, and write that in an equation in terms of x and y, and then relate x and y together so that we can get an equation for the area in one variable. And then we used our calculus techniques to figure out what the maximum value was at. And then finally, we went back to the original problem to figure out what x and y were. And what makes these optimization problems so tough is that no two are alike. Every problem is a little bit different, and you're going to have to relate the variables together in different ways every time. And the hardest part of these problems are not even the calculus parts, it's the setup parts. And while there's no formula or recipe that I can give you, I do want to give you a general outline that you can roughly follow every time. So I wrote up 6 steps that you can walk through when solving these optimization problems. And step 1 is to understand the problem, which sounds silly, but ask yourself, what is unknown? What are the given quantities? What are you trying to maximize? And what are the constraints? Questions like that just to set yourself straight before you dive too deep into the problem. After that, I would recommend drawing a diagram, even if it's something simple like a rectangle, just so you can visualize and get a sense of what you're actually trying to do in this problem. Step 3 is introduce notation, so begin to label things. Like in this problem, we had A was the area, X was the width of the rectangle, and Y was the length of the rectangle. After that, figure out what you're actually trying to maximize. In this case, it was the area, and write that in terms of the other symbols. So in our problem, it was the area is equal to the length times the width, which was x times y. And now if there's too many variables, the next step is to see if you can relate some of them together so that you can get an equation that only has one independent variable in it. And in this case, we had too many variables, that being x and y in the same equation. And so we related x and y by looking back at the problem and realizing that one of our constraints was that the perimeter was 100 meters. And so 2x plus 2y had to be equal to 100. And then finally, the last step is to actually do some calculus and find the absolute maximum or minimum values using the technique of finding the critical points and plugging in the critical points as well as the endpoints. And after you've done all that, make sure that you go back to the problem to ensure that you've actually answered the question that was being asked. And I know that this is tough. It's a lot to take in. In my opinion, this is actually the single toughest topic in Calculus 1. And so if you're struggling with this, that's expected. That's okay. So come on by office hours and we'd be more than happy to talk with you with these problems. And I'll do one more video on optimization just so that we can get some more examples because there are so many different types of examples. But I wanted this video to feel more like an introduction to optimization.